Good morning, this is Mr. Gusukuma. I hope you guys are having a wonderful extended break, staying safe out there. As for instruction today, we are going to be looking at polygons. A quick Google of polygons looking at images brings up a whole lot of different shapes. So one of the first things we're going to need to do is define these shapes so that you know exactly what kinds of polygons there are out there. To begin with, these regular polygons are named by the number of sides that they have. So the first several of them you should be very familiar with. But having access to the internet means you can get to all sorts of other names out there. Hendeca as 11 is not so oftenly used. Dodeca for 12 is fairly commonly used, along with triskaideka for 13, which goes to triskaidekaphobia, a fun word to say, and the fear of the number 13. And also icosagon, icosa being 20, is also commonly used. All of the quadrilaterals we've used so far are regularly shaped. That means that they had equal sides and angles. Here are some pictures of some that are not so regular. The other two categories then are irregular and concave or convex. Concave polygons, like the example for 6, 7, and 8 here, are polygons that have an interior angle that is more than 180 degrees. So in this example, that 210 is making this a concave polygon. Now if I were to move that point up, then you'll see this is now a convex polygon. So as a quick review, here's a whole bunch of information. We have regular polygons, the ones we're used to seeing for their classical shapes. We have irregular polygons, the ones that do not have equal sides and equal angles all the way around. We have concave polygons that appear to be falling inside of themselves, and convex polygons that are more robust or rounded. And lastly, we can also name each of these polygons based on the number of sides that they have, concave or convex. We can count all of the straight edges to figure out how many are making the closed shape that is a polygon. In case I forgot to mention it, poly does mean many, so polygons are studying many-sided figures. This is a straight extension of all the time that we spent studying triangles. So now we talk about some of the numbers that go with polygons. Right now I'm looking at the interior angles. We had intended to get to this at the end of the last section, so you've already seen this formula. It was thrown at you, but let me go back now and explain how we're getting all of our numbers. First off, you all know very well that the sum of the angles of a triangle is 180. So I wrote that down to remind you in case you forgot. And as we explore this, how many angles are in our other polygons, we're going to pick one vertex, one corner, and draw lines to the other vertices we can get to really separate these into a bunch of different triangles. So I'm not trying to think about this as one large complex figure, but rather I'm breaking this down into the shapes that we've already spent a lot of time studying. So what you will discover in this process as we start to separate these more-sided polygons, these many-sided figures into different triangles, is that every time we increase the number of sides, we add another triangle. So a quadrilateral can be split into 2 triangles, a pentagon split into 3, a hexagon split into 4, and so on and so forth. And the great, wonderful thing about this is that means that the sum of the angles for the entire shape is really the sum of the angles of every single one of its triangle. So a quadrilateral, let me label stuff real quick. So a quadrilateral is made of 2 triangles, each with 180 degrees inside of them. So a quadrilateral has 360 degrees total. A pentagon has 540, because that's 180 plus 180 plus 180. And a hexagon then has 720 degrees total inside of it. This sums up to be the equation n minus 2 times 180, where n is the number of sides. So that way a triangle, 3 minus 2 would be 1 times 180, that's one triangle. A quadrilateral would be 4 minus 2 is 2 times 180, because a quadrilateral was made of two triangles. A pentagon is 5 minus 2 is 3 times 180, because it was made of three triangles, and so on and so forth. So what I've started to do here, and what I would suggest that you do, part of your assignment that you do, is that you start to organize all of this information. So I've got names down the left-hand side of a table, just using their prefix. This is a great carryover into some of your other classes like sciences, where those prefixes will be important. The number of sides, of course, is going to be our n for our formula. The total of the interior angles is found by that formula, n minus 2 times 180, or, since we're going in order of number of sides, you can simply add another 180, another triangle to each shape. And then to find the amount of each angle, interior, inside angle, I've divided that number by the number of sides there are. So the 60 at the top right there is the 180 degrees of a triangle divided by the three sides. And the quadrilateral is the total 360 divided by four sides, which is also the same number of corners, vertices that we have. And then 540 divided by 5 gave us a 108 degree angle for the inside. Again, some of these numbers are going to show up very commonly, especially as you start to move to other subjects. So now that we have talked about interior angles, the angles on the inside of these polygons, I also want to talk about exterior angles, the angles on the outside of polygons. And for that, I'm going to use this wonderful animation. So the conclusion here, no matter how many angles we have or how many sides we have to a figure, the conclusion here is that if I were to collapse that figure down to nothing, look at just the exterior angles formed at each of those vertices, that we'd end up with a complete circle. And so for every polygon, the sum of the exterior angles is always 360 degrees. Or in other words, no matter how many times we make the angles going around the outside of a polygon, we always end up back where we started. Again, the idea of that complete circle, again, that fact you should know as 360 degree sum. So I have now completed the first four parts of the exterior angles by dividing the 360 total by the number of vertices. So in a triangle, each exterior angle of a regular triangle, equilateral triangle, would be 120 degrees. For a polygon, rather quadrilateral, a four-sided quadrilateral, regular is a square, so for a square, we'd have 90 degrees for each exterior angle, 72 degrees for each exterior of a pentagon, and 60 for each exterior angle of a hexagon. So to complete your notes, I would like that you go through the rest of the number of sides, 7, 8, 9, 10, 12, and 20. So as a brief review, this introduction to polygons has covered. Poly means many, so these are many-sided figures. They are extensions of adding a bunch of triangles together. We use that to find the number of interior angles, and exterior angles always had the same sum. That was more related to the circle than the triangle. We had a formula for interior angles, n minus 2 times 180, the total number of interior angles, that is. We know that we have several types of polygons, such as concave, the ones that look rounded, and convex. I said that backwards. Concave, the ones that look like they're caving in on each other, and convex, the ones that look like they're more circular, robust, round. And we have a bunch of new prefixes to learn that will carry on over through quite a few other subjects, especially the sciences. And you have a product that you should have created throughout this instruction, which is going to be a table that has the names, number of sides, total interior angles, each interior angle, and each exterior angle of regular polygons. That much information should be able to pretty quickly walk you through the first two assignments due on the 23rd, that's next Monday, about interior and exterior angles of a polygon and angles of a polygon.